Okay, in the last video we learned how to deal with salts as weak acids or weak bases. We're going to just do another example. So this is kind of a continuation of the last video. I just wanted you to have another example. So what we are doing in this video is, in this problem, is we have NH4Cl. Okay, when NH4Cl dissolves in water, you get NH4 plus and Cl minus. NH4 plus is the conjugate acid of NH3. NH3 is a base. We have a Kb value right here. And if it receives NH plus, it forms NH4 plus. So let's kind of do it like this. This is a base. NH4 plus is its conjugate acid. So because we are starting with what we can visualize as a conjugate acid, we have an acidic solution here. So the Cl minus just floats around. This is the reason HCl is a strong acid, is that Cl minus isn't a good acid or base. It just floats around. But the NH4 plus is a notable acid that we're going to need to do calculations with. So the NH4 plus water forms an equilibrium. And this is an acid. We said it was. We literally just got done talking about that. So this is an acid, which means it's going to lose an H plus to water. So the product should be NH3, which, not by much of a surprise, gives us information. We have useful information about NH3. And this is going to receive an H plus and form H3O plus, which means this is an acid. So we're going to need a Ka value for this. Okay, we don't have that. But we do have Kb of this, and these are a conjugate acid base pair, so it's basically going to be Kw divided by Kb. So to solve for Ka, it's going to be 1.0 times 10 to the negative 14th, and this is 1.8 times 10 to the negative 5th, and by absolute coincidence, it's exactly the same number as the last problem. And that's okay, it is what it is. Okay. So now we have an acid equation, we have a Ka, we can just treat the rest of it like a regular problem. Okay. Ice method. We are starting out with 0.100 molar. We can ignore water. This is 0, this is 0. This is going to decrease by some amount, and these are going to increase by that exact same amount because it's a 1-to-1-to-1 ratio. And this is going to be 0.100 minus x, and this is x, and this is x. We need to check our assumption to see if we can get rid of this x, because obviously that would make our lives easier. So let's do that. So since this is an acid, what we need to do is take the concentration divided by Ka, not this Kb value. So we take 0.100 divided by 5.6 times 10 to the negative 10th. And that value comes out to 1.8 times 10 to the 8th, which is significantly bigger than 100, so we don't have to do the quadratic. Okay. I can't guarantee you never will, but a lot of times for salts, the quadratic isn't really necessary because these Ka and Kb values tend to be so small that when you do this division, you tend to get really huge numbers, so notably bigger than 100. Okay. So as far as the math goes, Ka is equal to products over reactants at equilibrium, and we're using Ka because this is an acid. I know I've already said that like 4 times, but I'm going to keep repeating it, I guess. So Ka is products over reactants. Okay. Well, we have Ka, and we have the equilibrium values for those things, so we can solve for x. And the reason we're solving for x is it's the concentration of H3O plus, so we can solve for pH. So, plugging everything in, Ka is 5.6 times 10 to the negative 10th. This is x, and this is x, right? So I'm going to write this as x squared. And down here is 0.1 minus x, but because of the assumption, I can just write it as 0.1. We're assuming that x is negligibly small. Okay? So basically we're multiplying the 0.1 to the other side and then taking the square root. So x is equal to the square root of 5.6 times 10 to the negative 10th times 0.100. And that answer comes out to a pretty small number, 7.48 times 10 to the negative 6th molar. And the reason we solve for X, it is equal to the concentration of H3O plus. So to get the pH, we are going to take the negative log of that. Okay. And if you take the negative log of that, the answer comes out to 5.1. I guess for sig fig purposes, we probably only had 2 all the way through, but that's okay. So the answer comes out to 5.1, which is a pH below 7, which is definitely an acid, but it's a pretty weak acid. 5 is not super acidic. But that makes sense because this isn't a real strong acid. Its Ka value is pretty small. Okay. And it's not a stupidly high concentration, so not drastically different than the last problem. The trick on these is seeing what you have and how that compares to the information given. So this, we have a Kb of NH3. We don't have NH3, but we do have NH4 plus, which is its conjugate acid. Then treat the problem as such. So the extra step compared to any of the previous ice method problems is you have to realize that this is an acid, and you're also going to have to solve for Ka. The rest of this is identical. Okay. Thank you.